So, good day everyone. So, in this short lecture, we'll be looking at electronics and particle physics. Myself, Rishi Kumar, and Polar CAD will be exploring um, a lot about the preliminaries of particle physics and the modern experimental capabilities that we have as of today that enable us to translate our theoretical predictions to solid practical observations. Then we investigate the construction of these highly complex particle colliders, which are our experimental capabilities, which naturally leads us to appreciating the extensive use of electronic circuits in particle physics. So, I'd like to start off with a very brief introduction to high energy physics. So, defining particle physics, or in cooler term, high energy physics, they're both one and all the same, is a branch of physics that studies the nature of the particles that constitute matter and radiation in our universe. So, in more layman terms, it basically focuses on studying fundamental particles and interactions to explain their behavior. So, that naturally leads us to the question, what is a fundamental particle? So, a fundamental particle is one which we believe is truly elementary in its sense. In other words, it has no spatial extent, or it is a point particle and is not made of any more fundamental parts. Essentially, in pursuit of particle physics, we are trying to study these fundamental particles that exist within, let's say, an atom or a proton, because yeah, we thought that the proton or the atom was a fundamental particle, and then with more research we found out that the simple atom was made up of much more smaller particles, such as, let's take the electron or the protons and the neutrons inside the atom. But then more, as our particle colliders got better and better, we started to find a whole plethora of new particles, such as the one right here. It's called the standard model, which essentially allows us to categorize all of the particles that we find in our research in particle physics, through defining them through as quarks, leptons, and bosons, which are essentially categorized by their spins. So, for example, your quarks have half integer spin, and your leptons have integer spin. So that is a very small example of how the entire standard model, as of we know right now, is constructed and categorized. So yeah, now that we had a very small introduction into particle physics, we'll move on to the more relevant part in this lecture, which is collider physics. Yes, so as we all know, we have probably seen the Large Hadron Collider in many magazines, many news articles, and almost most pop science articles out there. So essentially, how does the Large Hadron Collider work? So there are going to be three parts to this. There's before collision, during collision, and the after collision mechanics in this collider uh, functioning. So we know that after photons and electrons, protons are the easiest particles to isolate and create a beam of, because protons are just atomic hydrogen nuclei. So to get a proton, we simply just ionize hydrogen and you've got yourself a proton. So how is this done? We essentially do this by taking hydrogen gas and putting it in a strong electric field. What this essentially does is that the proton and the electron are pulled apart because of the ionization effect. So once hydrogen is broken up, we can use electric and magnetic fields to essentially direct the protons to wherever we want it to move to. Okay. So what we do here in the what they do there in the Large Hadron Collider is they essentially isolate the protons that we want to collide, and then the LHC manipulates them with a radio frequency or an RF electromagnetic field. The protons are organized into collections of about 100 billion protons. Yes, 100 billion protons, and they are called bunches that sit in the troughs of the field. So essentially, we see a magnetic field, and at the center of that magnetic field we have the bunches. So these bunches have a size which is prefixed by the wavelength of the RF field and are separated in space from one another. The RF field in the Large Hadron Collider has a frequency of around 400 MHz, corresponding to a wavelength of about 3/4 of a meter. So the proton exists in isolation at the LHC, and it is always um, within a bunch, or else the proton isn't. There aren't individual protons; they are just a whole bunch of protons which are collected together by our RF field here. So, as a circular accelerator, which we can see here, right there, yeah. So the proton bunches can be sent around the circle many times to reach the desired energy. So yeah, so this is an advantage to linear collider. So a linear collider doesn't have a circle, so it is just one straight tube which uh, two bunches of protons are collided with each other. So the proton bunches can be sent around many times. Right? So which can probably or which can possibly lead to a greater acceleration of the protons, which lead to greater momentum of the particles and a higher chance of a successful collision. So even with the constant speed, protons traveling in a circle are accelerating because due to circular motion, and they always emit electromagnetic radiation, which are called synchrotron radiation. So a circular acceleration must input enough energy to both speed up the protons and maintain their energy, as they lose energy continuously through synchrotron radiation. So this is one of the main limitations on the energy to which the circular accelerators can reach. Okay. So the value of synchrotron radiation for the LHC, accounting for all protons accelerated, the power emitted from the synchrotron radiation is about a kilowatt. Um, that is, as we know what a kilowatt is. So there is no further explanation needed there. Yeah. So in addition to synchrotron losses from the protons traveling in a circle, we have to keep the protons in the LHC ring because, or else it will just stray off the path and essentially miss the entire collision itself. So this is accomplished by thousands of superconducting magnets that essentially bend the path of the protons without affecting their kinetic energy. So now that we have accelerated the protons and we have essentially contained them, so now we need to collide them. So the two counter-rotating beams, essentially consisting of thousands of proton bunches, are sent to collide at specific locations around the LHC ring. So as we see here, we can see there is a collision here, there's a collision here, and a collision there. So you can essentially choose places where you essentially want them to collide at, right? So, however, even though these bunches consist of billions of protons, the protons are very small, and the vast majority of the volume of a bunch is basically empty space. So the volume of empty space is around 30 orders or greater of magnitude greater than the volume of the protons themselves. So what does this essentially pose a challenge to us is that we cannot exactly pinpoint where or predict the collisions at which they're gonna actually meet at, right? So this is the challenge that we have here in almost all particle colliders. Right? So to improve this likelihood of protons actually colliding, we need to make the beam volume much smaller or make the bunches of photons much more compact. So how can we do this? This is accomplished at the LHC by quadrupole focusing magnets located around the collision points. Okay, so the bunch can be focused in both top, bottom, and left-right regions by stacking a series of quadrupole magnets that are rotated around 90 degrees from each other. Yes. So at the LHC, these quadrupole magnets can focus the beam down to a width of around less than 10 micrometers. Therefore, at the collision point, the volume of the punch is reduced to around 10 to the power minus 8 meter cube. So we can see how much we have essentially made our large proton bunch into a very compact beam. So once the proton beams have been accelerated to the maximum energy and focused at a collision point, so essentially what happens, the two beams essentially just meet in layman terms and they explode into a shower of particles emanating from the collision point. So that is at collision. So we can see the two beams enter and they essentially scatter into a huge shower of particles right there. So yeah. So the dynamics of what happened at the moment of the proton collision is imprinted in these final state particles. So we know what happened at the end. So we can essentially trace back what happened before that. So how is that imprint essentially um, visible in the final state of these particles? They're imprinted through energy and momentum conservation or through angular momentum conservation and charge conservation of these particles. So using that experimental data, we can essentially retrace using basic calculation, not basic, but then basic enough in the sense. So to measure what happened before the collision. So at a particle physics detector, we are able to measure many particle properties, but there are many others which aren't easy to measure or which we don't simply try to measure. For example, energy and momentum conservations are pretty easy to find out, but then, and another point is electric charge. Electric charge is also very easy to measure, but then angular momentum of or intrinsic spin is not easy to measure because it is intrinsic and usually just manifests themselves in symmetries. So what do? We do not waste our time trying to make detectors which are sensitive to spin. So what we have essentially moved into here is our detection and our detector components. Yes, so let's move on to how to measure the particle properties from the various components of the detector. So we will work with a much simplified picture, which the Atlas and the CMS are both equivalent. So the Atlas and CMS are two sections of the Large Hadron Collider, as we know, right? So the experiment consists of many layers, essentially, which each of which measures particular properties or is sensitive to particular particles. We'll see that in the next slide here, but then let's just take a moment to appreciate how this entire collision chamber is essentially built. So there are the muon chambers, which essentially, as we'll move on, we'll see how these muon chambers work, and then we can see the magnets there, and this and the semiconductor trackers for the particles, and we have the pixel detector and the calorimeters. Ah, yes, this is another topic that we will touch in the forthcoming slides. Just a second. Yes, so coming back. So yeah, where was I? Yeah. So these we're gonna look at the tile calorimeters very soon in the next coming slides. So essentially, detectors like Atlas or CMS are often referred to as 4 pi hermetic detectors because they capture all the particles produced from the proton collision throughout um, 4 pi steradians of the sphere as possible, or in much simpler terms, it tries to capture all of the data that happens within this structure right here. Um, so yes, what although we can assume a very ideal scenario, but this is impossible because the proton beams come in from somewhere and the cables have to go somewhere. Uh, or else otherwise the coverage is very exceptional. It is used to produce the results of very minimal error and calculations with very less, with very high accuracy. As we go on, we'll see the statistical significance of our results, which will come in the next section of this lecture. So, immediately outside the region of the collision point and the proton beams is the tracking system. So, the tracking system consists of millions of individual channels that respond when a charged particle hits them. So, they're basically detectors. So, these channels consist of silicon or gas that ionizes when a high energy particle with charge passes through. This ionization is recorded at numerous points along the trajectory of the charged particle and traces out a track of the charged particle. As we see here in this diagram, it's very beautifully illustrated. So observing these tracks provides information about the direction of charged particles, but by itself doesn't provide the information about the energy of the particles. So what makes the tracker especially useful is that it is embedded in a solenoidal magnetic field, as we saw in the previous thing right there. Yeah, there is a solenoidal magnet right there. So the solenoidal field points parallel to the proton beam. So the charged particles' trajectories are affected by the magnitude of their charge and momentum p. So the greater their magnitude of charge, the greater the deflection or the deviation of the particle there of it will have from the initial beam. So the only component of momentum perpendicular to the magnetic field is affected by the magnetic field. Because of this, the solenoidal magnetic field, the tracking system is sensitive to both the charge and the transverse momentum of the particles. The tracking system consists of many layers of material away from the interaction point. Curvature can be determined by a minimum of 3 hits, although the tracking system typically has about 30 layers for redundancy, just for safety. So importantly, it is the curvature, not the radius of the curvature, that is more easily measured. So the curvature is just the inverse of the radius of curvature, which is inversely proportional to the transverse momentum. Yeah. So the next layer of the particle detector, onion, as you see, is the calorimetry. So the calorimetry, the essentially is are made up of electromagnetic and hadronic calorimeters, but they have the same function. They are designed to be sensitive to many different types of particles. The calorimeters are designed to stop particles and have them explode all of their energy into the individual cells of the calorimeters, which essentially allows us to measure how much energy each of these particles have. So the electromagnetic and hadronic calorimeters are sensitive to electromagnetic and hadronic radiation respectively. In particular, the electromagnetic calorimeter stops electrons and photons and low mass particles that interact via electromagnetism. The most important way that the electromagnetic calorimeter stops high energy electrons and photons is through a small process called it's just pretty hard to pronounce, it's Brimstone process. The Brimstone process is the process by which an electron emits a photon which decreases its energy. In a similar way, a photon can split into an electron-positron pair, each resulting in each resulting particle has less energy than the initial photon. So at Atlas, for example, the electromagnetic calorimeter consists of lead plates immersed in liquid argon. So they are argon calorimeters. The liquid argon ionizes and the energy of the low energy particles can be measured efficiently. The lead plates have strong stopping power for more energetic particles. So together with argon, they form the electromagnetic calorimeter and stop nearly all electrons and photons created in the collision. So the hadronic calorimeter acts in a much the same way as the electromagnetic calorimeter. However, it must stop particles with a much higher mass than electrons. So hadrons like pions, for example, interact more strongly with atomic nuclei and not atomic electrons. As such, their interactions are much complicated to understand. But the same principles are at work here. Hadrons pass through material and lose energy by inelastic collisions with atomic nuclei, and then which allows us to measure the total energy that the hadron possessed in the first place. So the hadronic calorimeter consists mostly of iron for stopping and plastic scintillators that are used to measure energies of hadrons. So yeah, so electromagnetic calorimeters measure the energy of electrons and photons as they interact with matter. Hadronic calorimeters sample the energy of the hadrons, such as protons and neutrons, as they react with atomic nuclei. So that is just a very small uh, summary of what I said about the calorimeters. So outside the uh, Atlas and CMS is a muon detection system. So at Atlas, it consists of detectors for tracking in a high Tesla toroidal magnetic field. CMS, by contrast, uses a high Tesla solenoidal magnet to bend the muons. So essentially, uh, we have stopped all of the particles, such as, let's say, the hadrons and or what you call that, hadrons and the photons and electrons. But then what isn't stopped is are the muons. So what we can efficiently do is that we essentially keep the muon detectors at the end or at the last end spectrum right there. As you see the muon spectrometer there, after the hadronic calorimeter and our electromagnetic calorimeter, we have our muon spectrometer. So why are detecting muons by themselves are hard, but then now it is made easy because we have essentially stopped all particles other than the muons themselves. So essentially, any particle that passes after the hadronic calorimeter has to be the muons. And then, as you notice that we missed one critical particle here, which is the neutrinos. So it is very hard to directly measure a neutrino, or almost we can say that it's impossible. But what the neutrino does is that it essentially leaves traces of energy, or essentially as we measure these systems, we notice some missing components of energy or some discrepancies in our data. So that is essentially compensated by the neutrinos. So that is how we can detect neutrinos from indirectly detect neutrinos, and not essentially directly use a detector to track the neutrinos themselves. So yes, now we come to the post-collision. I think we have finished our collider physics. Now let's go into the statistical analysis that are present in the uh, entire contraption. So we before we go into the mathematics here, let us just simply just take a moment to analyze what a statistical analysis is. So any experiment that we do, there it is bound to have some degree of error. So if we take a measurement of, let's say, a pencil, it has a very basic error of, let's say, plus or minus 0.1 millimeter. But that is for a pencil. So any macroscopic or microscopic experiments are bound to have some degree of error or statistical discrepancy in them. So we are now looking at a large experiments that we have done throughout our course. But then for high energy physics, these microscopic interactions are very hard to actually analyze the statistics within them. So how do we tackle this, or how do we know that this isn't just or let's say we find a new anomaly in our collision. So how do we essentially pinpoint that, okay, look, this is an actual new particle that we found here, or maybe it is just some detector or some random error. So that is why we use our statistical analytic methods. So we are going to be looking at some of that just for completion. So we know that we can see the normalized distribution right there is simply the integral right there, and the normalized distribution over a finite region is over there, which is equation number 2, which is said to be always greater than 0. And our normalized distribution is simply that our probabilities always add up to 1, which is a very simple statement that we have learned in schools and colleges and everywhere we go. So yes, so we use this very efficient method called the bin approximation. So what do we essentially do? We essentially create a histogram of our number of events, and then we use this curve fitting, or which is called the bin approximation. We use that to essentially construct a line graph or a continuous function from these bins, let's say. So we can see here that how we construct our bins. This is NEV is the number of events, and delta X is our time interval between them. And then this is just a summation. And the normalization condition here is that all of them must be equal to 1. However, so if we take the limit as number of events tends to infinity, and then the delta X, or the width of the each bin, tends to 0, we essentially get a perfect, let's say, it's similar to the integration and the numerical integration methods that we've done before. We essentially construct uh, bar charts or bins, and then we limit them to 0. So then we essentially get a continuous integral of the probability function at hand. So that is essentially a very short um, intro into a bin approximation. And then this is again a small refresher into our binomial expansion, which we again use for our statistical analysis. So let's say we know the binomial expansion is just pk equals p par k 1 minus p, which is the probability, nev minus k, nev being the number of events, and into this nev by k. This is a very it's just convention that we write it as nev by nev and k. So we know this, that nev and k is just a number of events by k factorial into number of events minus k whole factorial. So this thing right here is called the binomial probability distribution, since it represents an expansion of the binomial expression x plus y whole power n equals the summation xi y n minus I and I. I'm not going to be explaining too much of this because that is not a focus here, and we have already studied binomial expansion in our first and second year courses. So what I am going to look at is the Poisson distribution. So again, the Poisson distribution will be useful here for calculating or constructing the Gaussian distribution, which essentially enables us to determine the standard deviation of any value that we have, which enables us to find out the statistical relevance of our results. So I'm not going to explain too much of this, just we can just take a look at here. So the limit minimum of NEV and K, it is essentially a more refined version of the binomial distribution. And I think we know how the Poisson distribution looks like. I think we have an image there. Uh, so yeah, so it is essentially it looks like a bell curve, right? So, and then what we also do there is, uh, yeah, so the mean and expectation values, this is pretty simple. The expectation value of K is simply just number of events into the probability. And the sigma square right here, so sigma being our mean right there. So the mean is just the root of number of events into the p, which is the probability. Yeah. So now that we've seen that, let us look at this small event called the Diphoton Axis. So what was the Diphoton Axis? This is just a Feynman diagram. So we don't need to really understand this. This is just put here for a pictorial representation of this Diphoton Axis. So the diphoton axis in particle physics was an anomaly that was found in 2015, which we thought was an indication of a new particle resonance. But in the end, it ended up, or still we are yet to find out that it was either a statistical anomaly or whether we actually found the particle, we are not yet sure. But this diphoton axis essentially implies a particle called the di gamma. so which essentially decays into two photons, so which is called the Diphoton Axis. So significance in discovery, I think I need to speed up a bit here because Pugel needs to come to the meat of the entire lecture right here, which is the relevance of electronics in all of this particle physics. The central limit theorem is just this equation right here, which is that as NeV whole power k by k factorial, e power negative NeV p essentially tends to p of x, which is our probability. So where our p of x is this function right here. So we have essentially simplified our Poisson distribution right here, number 12, into this new form called the Gaussian distribution, which essentially allows us to find out the exact probability and with respect to x without leaving the k out here, and then which essentially helps us for calculating any statistical anomalies, as I said before. So as always, we need to normalize this function. So we implied that the Gaussian function is normalized, which makes our calculations even more simpler. So yes, now let us use a practical example. So let's calculate the probability that there was a deviation that was at x sigma above the mean. So x is just any number above sigma. So sigma is the standard deviation. So this is called the p value of deviation and requires integrating from n plus x sigma. So x can be 1, 2, 3 is equal to n plus x root n to infinity. So px is just simply this integral dx of this expression, and so if we simplify that, we get px is equal to integral infinity to x dx is 1 by root 2 pi exponential e power x squared by 2, negative x squared by 2, mind you. So this integral can be evaluated in terms of the error function, which is a very important function we have. So px is just 1 by 2 minus erf, which is the error function of x by root 2 whole by 2. Yes, so once we found out the deviation, so how is this relevant in our scientific discoveries? So any discoveries that we do right here, so any any result that we got that is greater than 3 sigma, with sigma right here implying deviation, any 3 sigma greater than our mean is essentially told to be an anomaly, or we essentially disregard it. But then anything within, let's say, 1 sigma, 2 sigma, we can take that as a valid reading, and then we continue with our calculations from there. So from now on, from now I am gonna, there's just a Higgs mechanism that we found in our statistical calculations. I'm not gonna explain too much about this, but this graph was just a small indicator of how we can see this anomaly right here and how we essentially fit the curve from this entire thing. And we actually found out that the Higgs boson was actually not a statistical anomaly, but was an actual particle uh, through this statistical analysis method. So from now I'm going to lead the stage on to Pugalaarasu, who is going to be talking about the electronics that are involved in this entire Large Hadron Collider project and how we use that